Okay, before you watch this video, please go over the practice lab exam, do every single question, and then watch this video. And I'm going to go over every single question with you and teach you not only how to do the problem, but also how to approach every single problem. All right, let's do this. So again, please do this before you watch the video. You get a lot more out of it. So the first problem. When you read the first problem, you go, okay, the first problem is a titration problem, right? After you read the problem, you go, okay, I know this one. This is a titration problem. Now, every time I have a titration problem, what I like to do, I like to draw it out. I like to draw it out because it makes it easier for me to do the problem. So I'm going to draw a burette, and I'm going to draw a flask over here. Now, when you read this problem, so what you have a sample of an acid. The acid is H3X, okay? So I have an acid. The acid is H3X, and you have 5.21 grams of it, okay? And what you're doing, you're titrating it with sodium hydroxide. So what I have up here, I have sodium hydroxide up here, and the sodium hydroxide has a concentration of 0.447 molar, okay? And you add 16 ml of it before it turns pink, right? It reaches the end point. So how much you add? You add 16.00 ml of sodium hydroxide, and it turns pink. So far, so good? Okay. Now, what the question asks you, what is the percentage of H3X? Now, this is a hard problem, and I wanted to give you a hard problem to get ready for the lab exam. Now, a few things. In this problem, I don't tell you what the acid is. I said the acid is H3X. That's okay. It doesn't matter what the X is. The second thing, I ask you for the percentage of acid. Now remember, percentage usually means gram percentage. So percentage usually means gram percentage. So far, so good? Okay. Now, almost every single titration problem that you have, the beginning part is the same. You have to figure out how many moles of NaOH you added when it turns pink. And then from that, you can figure out how many moles of the acid you had. So the first thing we need to figure out how many moles of NaOH we added and when it turns pink. Now, I have the molarity. Remember, I need you to say this after me. Molarity is moles per liter. Molarity is moles per liter. Don't forget that. Molarity is moles per liter. Now, usually they have to give you the molarity of NaOH, and you know how much NaOH you added. So, you have the molarity of NaOH, as you can see right here, and you know how much NaOH you added. So you have the molarity and you have the volume. So you can figure out the moles. So the molarity is 0.447. I don't know how much NaOH I added, but I know the volume. The volume is 16 ml. You need to convert it to molarity because molarity is moles per liter divided by 1,000. You get 0.01600 liter. Now, if I solve for X, what I end up getting for X, I get 0.00715 moles of NaOH. Again, I knew molarity is moles per liter. I have the molarity of NaOH. I have the volume of NaOH. I can plug it in. I can solve for X, and the X would be the moles of NaOH. Okay, so we know how many moles of NaOH we added, and then it turned pink. Now the question is, how many moles of the acid we had. If this was a monoproduct acid, we would be done. The same number would be the moles of the H3X. But this is not a monoproduct acid. What is this acid? I give you a hard problem. That's good. I have H3X. H3X is not a monoproduct acid. It's a triproduct acid. What that means is one acid has how many hydrogen? One acid has 3H plus. Now this is very key. One acid, because it's a triproduct acid, it's H3X. One acid has 3H plus. So to neutralize one acid, to cancel out one acid, how many NaOH do I need? I'm going to need 3 NaOH because one acid has 3H plus. So one acid has 3H plus. So for me to neutralize one acid, I'm going to need 3 NaOH. So far so good? Okay. So what I have here, 0.00715 moles of NaOH. But I know that since I have a triproduct acid, for 1 moles of the acid, I need 3 NaOH. So for 1 moles of H3X, I need 3 moles of NaOH. I want to go over this one more time to make sure you're really, really clear on this, because one acid has 3 hydrogen, so I would need 3 NaOH to cancel out those 3 H pluses. Alright, so the moles of NaOH cancels out. I end up with moles of the acid, and the moles of the acid would be 0.00238 moles of H3X. Okay? Alright, I know you know this, but just for me, one more time I want to go over this. So one acid had 3H plus, so you needed a 3 NaOH, so you would have 3 OH to neutralize out the 3H plus. Okay, so I have the moles of the acid. Alright, so now remember, every titration problem, the beginning is the same. You figure out the moles of NaOH, you figure out the moles of the acid. Now the last part, they ask you for percentage of the acid. We said percentage is a gram percentage. Percentage, it usually means gram percentage. I have the moles. What I need to do, I need to convert the moles to grams. You know how to do that. Okay, tell me, how do I go from moles to gram? How do I know from moles to gram? I use molecular weight. Well, the molecular weight of the acid is given to you in this problem. 1 mole of H3X, they say, is 195 grams, okay? What we get is 0.465 grams of H3X. Okay, pretty good so far. So now we have the grams of the acid. Again, we don't know what the formula of the acid is. It doesn't matter because they give you the molecular weight. That's all you need. All right, now we said percentage is a gram percentage. So now what we're going to do, what we have here, we have 0.465 grams of the acid. Now, how much was the entire sample? The entire sample was 5.21 grams times 100. So the entire sample was 5.21 grams. And from that, 0.465 grams of it was the acid. So if I divide them together times 100, I'm going to get a percentage of the acid, the gram percentage. So this is how much acid you have. This was the entire sample. Entire sample, how much acid you have. Now, don't forget about sig fig. How many sig fig I need? I'm bound to 3 sig fig, and it will be 8.92%. I have 3 sig fig because the molarity is given to you in 3 sig fig. Yeah? This was a big problem. Now, one thing I want you to keep in mind, okay? One thing I want you to keep in mind, in your lab, what you use ascorbic acid. use ascorbic acid in your lab. And ascorbic acid is a monoprotic acid. Ascorbic acid is a monoprotic acid. Now, what does that mean? That means the ascorbic acid that you use in lab had only one hydrogen. So the mole ratio between ascorbic acid and sodium hydroxide would be 1-to-1 ratio because ascorbic acid had one hydrogen. It has a crazy looking formula and it sounds cool, ascorbic acid. You might think it has more than one, but no, it's monoprotic acid. So if this problem was done, and if you had this problem with asking about ascorbic acid instead of H3X, it would have been monoprotic acid, 1-to-1 mole ratio. So far, so good? All right, beautiful. Let's go to the next problem. Here is the next problem. Next problem is a redox. You know redox. I know you know redox, but let's go through it quickly together. So I have a redox reaction. Now, what I'm going to do, you have to supposed to balance it. So we're going to write 2-half reaction. Sn plus 2 goes to Sn plus 4. Iodate goes to I2. Okay? Right, 2-half reaction. You balance everything except oxygen, hydrogen, and charges. Okay, so let's balance everything except hydrogen, oxygen, and charges. I have one Sn. Sounds good. There is no oxygen. There is no hydrogen. Makes my life easy. That's good. Let's not question it. Let's come on down here. 1I, 2I. I have 1I, 2I. The first thing I need to do, I need to add a 2 over here because it balanced everything except oxygen and hydrogen and charges. So I have 1I, 2I. I added coefficient here. Now I have 2I and 2I. Perfect. Now you balance the oxygen by adding water. How many oxygen do you have here? Pay attention. It's not 3 because you added a 2 over here to balance the iodine. So I have 6 oxygen now. So I'm going to add 6 H2O. So you add the oxygen, you add water to balance the oxygen. Okay, so you balance the oxygen by adding water. Now what do? We balance the hydrogen by adding H+. How many H+ do I have on this side? Nothing on this side. On this side, I have 12, right? 6 times 2 is 12. So what I'm going to do, I'm going to add 12 H+ on this side to balance the hydrogen. Okay, so we balance the oxygen, we balance the hydrogen. The last part is balancing the charges. And to me, that's the most difficult part. Okay, so let's balance the charges. Let's go up here. The charge on this side is plus 4. The charge on this side is plus 2. You balance the charges by adding electron, but because electrons are negatively charged, you add it to the more positive side. So here I have plus 2, plus 4. This is my more positive side, so I have to add the electron to that side. Okay, now how many electrons do I add? I add 2 electrons. Again, electrons are negative, right? So plus 4 plus 2 minus, this would be plus 2. It would match up this part that is plus 2. The point is we want to make sure the charges are the same on both sides. Let's come down here. Okay. All right, let's go down there. If we go down here, what's the charge on this side? So pay attention to this. I have 12 pluses and 2 minus. 12 pluses and 2 minus. So the charge would be plus 10. Let's go down up here. I have 0. I2 has no charge, neutral compound. Water also is neutral compound. So no charge, no charge. I have 0. Okay. All right. So far, so good. Now, this is my more positive side. So I'm going to add the electron on this side. Now, how many electrons do I add? I have 10 over here. I have 0 over here. Remember, the whole point is you want the charges to match up. So I want to add 10 electrons to this side, because if I do that, plus 10, minus 10, 0, it would match up that. All right, beautiful. So we balanced the charges too. Now, let's go to the last part. Here's the last part. Remember what I said? I said if I lose $5 and if you find it, how much money did you find? $5. If I lose $10 and you find it, how much did you find? $10. It's the same idea with charges. If one loses 5 electrons, the other guy has to find 5 electrons. If one loses 10 electrons, the other one has to find 10 electrons. But if you look over here, this guy lost 2 electrons, but this guy gained 10 electrons. These two have to match. You lose 2, the other one gets 2. You lose 10, the other one gets 10. So these two have to match, and they don't match. That's okay. We can make sure they match. How do we do that? What if I multiply this by 5? If I do that, then this would be 10. It would match up this one, right, which is also 10. Except when you multiply the electron, you have to multiply the whole thing. You have to do the whole equation. You can't just multiply just the electron. You have to multiply the whole equation to 5. All right? So then 10, 10, we're good. The last thing you're going to do, remember at the beginning, we broke it up into 2 half reaction. We're going to combine them back together. Let's combine it back together. So we're going to add all the reactant together. We're going to add all the product together. The only thing, don't forget, you have to multiply everything by 5 on here. So, do this with me. I'm going to get 5 Sn plus 2. I'm going to come down here, plus 10 electron, plus 12 H pluses, plus 2 iodate. Now what I'm going to do, combine all the product together. 5 Sn plus 4 plus 10 electrons plus I2 plus 6 H2O. Now you need to cancel out anything you could cancel out. Now remember, at this point when you get here, if you cannot cancel out the electrons, ooh, that is bad. Something went wrong. So at this point, you must be able to cancel the electrons out. Okay, we cancel the electrons out. So far, so good. All right. So the question asks you, what's the reducing agent? What's the oxidizing agent? If you remember, I gave you a shortcut. The shortcut I call the RR rule. What was the RR rule? The RR rule said if you add electron to the right, if you add electron to the right side, that is reducing agent. So that's why we call it the RR rule. If you add electrons to the right, that's a reducing agent. Now remember one thing for me. I need you to remember this. That reducing and oxidizing agent, the agent are always on the reactant side. So you have a 50-50 chance. Don't look at the product. Agent, those are the things, the reagent are doing this stuff. They're doing the oxidation and reduction. So the agent are always on the reactant side. So you have a 50-50 chance. One is oxidizing agent, one is reducing agent. So let's look at the RR rule because that's a good shortcut to save you time on the exam. If you add electrons to the right, which equation we add electrons to the right? Bottom, we add it to the left. The top equation, we add electrons to the right-hand side. So you add electrons to the right, that means this is my reducing agent. That means this is my reducing agent. So my reducing agent would be Sn plus 2, which means the other one, the iodate, is going to be my oxidizing agent. So far, so good. So that was the shortcut. Now, I want to also show you not the shortcut, the longer way. When you look at this equation, okay, I'm actually going to write it over here. Let's say we have Sn plus 2 plus iodate minus going to I2 plus Sn plus 4. Now, if you want to figure out what's the oxidizing agent or reducing agent, again, this was a shortcut. The shortcut is a good way to confirm what you wanted to figure out without balancing the equation. Well, check this out. Here, you have Sn plus 2 going to Sn plus 4. even from +2 to +4. What happened? When you go +2 to +4, you became more positive, right? When you become more positive, that is oxidation, right? You become more positive, that's the oxidation. Now remember, if you get oxidized, you are reducing agent, or the opposite. Okay, so if this one got oxidized, which means the other one has to get reduced, but let's go over it anyway. So I'm going to come down here. The charge on I2 here is 0 because I2 is a diatomic molecule. There's this neutral diatomic molecule. That's how they exist in nature. And the charge is 0 on I2. All diatomic molecules have a charge oxidation number of 0. Now, what's the oxidation number of iodide over here? We need to figure it out. Okay, so the entire thing equals -1. Oxygen is always -2 times 3 is -6. This is I. So if I figure out I know you know how to do this, but I'm going to go over it anyway. I will be +5. Okay, again, this one was super easy. And do the easy one. And if this is my oxidation, the other one has to be reduction. You don't really have to do it, but I want you just to do it to get more practice. So I2, diatomic molecules, they all have an oxidation number of 0. So I know I is 0 over here. I need to figure out the oxidation number of I over here. What I can do, it's a covalent compound. I can set it up like this to figure out what I is. The entire compound equals -2. I know oxygen is always -2 times 3 is -6. I can figure out I is +5. I go from +5 to 0. It became more negative. That is my reduction. That's good. So it matches up. So if this is oxidation, this is going to be this is reduction, this is going to be my oxidizing agent. And this match up what we had with the shortcut. And the shortcut is great. It saves you some time on exam. All right, great job. Let's go to the next problem. Now for this question, they ask you the one that contains the smallest mass of fluorine. Now this question, you can't just look at this and pick one. You actually have to do the math and convert everything to the moles of fluorine or the mass of grams of fluorine, and then decide which one is the smallest mass of fluorine. And if you get a question like this, it's going to take you a long time to do this. So it's always good to do these kind of questions at the very end when you have extra time. All right, so let's do this. So here are the options. The option is I have 1.00 moles of FeF3, okay? The other option is I have 9 times 10 to the 23rd molecules of HF. And then I have 172 grams of titanium fluoride. All right, what I'm going to do, I want to convert everything to moles of fluorine or mass of fluorine, and then decide which one contains the smallest mass. All right, so let's do this together. All right, so the first one is, again, they give me the moles of FeF3. I have to do a mole ratio because what I want at the end, I want the mass of fluorine. They give me FeF3, but they ask me for fluorine. They give me one thing, they ask for something else. Of course, we have to use hashtag mole ratio. Now, I'm already at moles, which is kind of nice. I'm already at moles. So now I'm ready to do the mole ratio. I don't want the mole of FeF3. What I want is mole of fluorine. Because again, the question asks you, we pick the one that has the smallest mass of fluorine. Alright, so what is my mole ratio here? For 1 mole of FeF3, how many Fe do you have? How many F do you have? You have 3F. So in 1 mole of FeF3, you have 3 moles of F. So far, so good. Again, you can stop here and compare the moles. That would be the same thing. But I'm actually going to go all the way to grams. Now, I have moles of F now. 1 moles of F is 19.0 gram. So I can go all the way to the mass and convert it to that. Again, moles of Fe, F3 cancels out. Moles of F cancels out. What I end up with 57.0 grams of fluorine. Alright, now the next one. The next one gives you the molecules of FHF. Again, remember, they give you one thing, you want something else. What you are looking for fluorine, but they give you the HF. What do we have to do? Yeah, hashtag mole ratio. Every time you have one thing but you want something else, mole ratio is what you need to do. Except I don't have moles right now. I have molecules. Well, that's okay. I can convert molecules to moles. That's not a problem, right? How do I do that? Avogadro's number. So 1 mole of HF would be 6.02 times 10 to the 23rd molecules. Okay. Now I have moles. Now I can do a mole ratio. I don't want the moles of HF. What I want is moles of F. What's the mole ratio? Let's look over here. In 1 moles of HF, how many F do you have? You have 1 F. So the mole ratio is 1 to 1. Again, and I'm going to go all the way to math. You can stop here and compare moles too. That would be the same thing. Then 1 mole of F, still 19.0 gram. Alright, this is good. So the molecules cancel out. I end up with moles. So I could do a mole ratio and get what I want, which is moles of F, and then go all the way to gram. If I do that, what I end up getting is 28 grams of F. Okay. Now last one. Again, the same thing. I have 172 grams of titanium fluoride. Now what I'm going to do, I need moles because what I want is just fluorine and not TiF2. So you have to do mole ratio. But before I can do a mole ratio, I need to have moles. So grams needs to cancel out, and I'm going to convert it to moles. 1 mole of TiF2 is 85.8 grams. Okay, so that's good. Now what I have now, so now I have moles of TiF2. Now I can do a mole ratio. Again, I don't want the moles of titanium fluoride. What I want is moles of fluorine. What's the mole ratio here? Tell me. In 1 mole of TiF2, how many F do you have? You have 2F. So in 1 mole of TiF2, I have 2F. Again, I'm going to go all the way to grams. You can also stop at mole and compare because they're all going to be multiplied by 19.0. So you can also do that too. But I want to go all the way to mass to get more practice. So the grams cancel out the moles of, what did I just do? The moles of titanium fluoride cancel out. I had moles of F, and I went all the way to grams. I have 76.1 grams of F. Alright, so I converted everything to mass of fluorine because that's what they asked me. Now I can compare. So which one contains the smallest mass of fluorine? That would be this one right here, right? Because I have 57, I have 28, 76. So my answer would be this one right here. And there is no way you would have been able to tell just by looking at this. You would have to do the math. Now, does this take a long time? It does take a long time. This is why if you have a question like this, I highly recommend you to do this at the end when you have extra time. Now, before we move on from this question, I want to make sure that you write this down on the exam when you take in the exam, and every time you do any problems with chemistry, remember gram goes back and forth to moles, and moles goes back and forth to atoms, molecules and ions. Don't forget that, right? And to go from grams to moles, of course, we use molecular weight. To go from moles to atoms, we use Avogadro's number, 6.02 times 10 to the 23rd. And every time they give you one thing, but they ask for something else, what you have to do? You have to do hashtag mole ratio. Mole ratio is really, really key. And that's why it gets a hashtag. And you have to have moles before you can do a mole ratio. Alright, so don't forget this. Everything comes back to this. Okay, let's do next problem. Okay, so for this problem, they ask you what is the oxidation number of Si in H2SiO3. Alright, do you know how to do this one? So, what they gave me is, let me rewrite it, H2SiO3, and they ask you to figure out the oxidation number of Si. Okay, so what are we going to do? What we're going to do, we are going to equal the whole thing to 0. Why? Because this is a neutral compound. It has no charge, so the entire compound is going to equal 0. And remember from lecture, oxygen will always be -2, and hydrogen will always be +1. So oxygen will always be -2 oxidation number, and hydrogen will always be +1 oxidation number. There are a couple exceptions. We're not going to worry about that, but most of the time, oxygen is -2 and hydrogen is +1 oxidation number. Doesn't change. So I have 3 oxygen times -2. That would be -6. I don't know what Si is, but I do know hydrogen is always +1 times 4 would be +4. So now I can just do math and figure out what is going to be the Si. So +4 plus Si -6 equals 0. Now, let's do math. So I would take the 6 over here. It would be +6. I would take the 4 over here. It would be -4. Then Si would equal to 2. So far, so good? Okay. Alright, next one. Next one says, what is the percentage of sulfur in SO3? Every time I have a question like this, people tend to overthink it. Don't overthink it. Percentage of sulfur in SO3. Okay, how many sulfur do you have? You have 1 sulfur. I don't remember what we said. We said percentage usually means gram percentage, right? So I have 1 sulfur in here. And the molecular weight, the molar mass of sulfur is 32 over. Now, so this is the mass of sulfur over the mass of the entire thing, the mass of SO3. And if you look it up, the mass of SO3 is 80. So 32 divided by 80 times 100. What you end up getting? You end up getting 40%. So basically what we did, it was the mass of sulfur over the mass of the entire thing, SO3 times 100. That tells you the percentage of sulfur in SO3. Okay. All right. Beautiful. Let's move on. Next one is a little tricky. It says 3 metal ions that do react with H2. What do you need for this question? They give you metals and metal ions and ask you which one are going to react. What you need for this one, you need the activity series. And the activity series is going to be given to you. So what you need the activity series for this one, and that's going to be given to you. I know I've gone over it. I know you know how to use the activity series, but we're going to go over this question in detail to make sure you got this down. Okay, so here is my activity series. Now, they ask you which of these metal ion, will react with H2. So let me find H2 first. Okay, here is H2. H2 is right here, okay? Now, let me look at the metal ions. What do I have? They have chromium, silver, mercury, magnesium, manganese, and copper. All right, I'm going to come over here. So the ones that we're talking about was manganese and magnesium, and it was copper, mercury, and silver. Okay, so far so good. All right, so now here's the thing. They say which one is going to react with H2. Okay, so I have H2. If I have H2, what is going to happen to H2? H2 is going to become H plus. So H2 is going to become H plus. What happened to H? What happened to hydrogen? The oxidation number of H2 is 0. That's a diatomic molecule. Diatomic molecule have an oxidation number of 0. So H2 has an oxidation, so hydrogen has an oxidation number of 0, and here it's plus 1, right? So even from 0 to plus 1, so it becomes more positive. So that is oxidation. Now, if H2 is being oxidized, what does that mean about metal ions? So metal ions, again, they're metals that have charge on them, right? Because they're metal ions and metals are cations. So what would happen to the metal ions? The metal ions have to get reduced. Okay? Again, this question, they give you H2 and metal ions. So if I have H2 has to go to H plus, so it's going to get oxidized. Now if I have metal ions, and metal ions are positively charged, they have to get reduced to become metal. So far so good? Okay. Now remember what we said about this activity series. Here is the deal. In order for a redox reaction to go, what gets oxidized has to be higher on the activity series than what gets reduced. Because the ones over here, the one on top, they really want to get oxidized. The one on the bottom, they don't really want to get oxidized. You already know that. Why do we use gold jewelry? Because gold jewelry doesn't want to get oxidized, so it's going to stay shiny and nice for a long time. This is why we use silver as a jewelry, because silver jewelry does not want to get oxidized. It would stay nice. This is why we don't have zinc ring or zinc jewelry. That's not going to end well, right? Because they want to get oxidized. It's not going to be nice after a while. So the guys down here, they don't like to be oxidized. The one on top, they really want to be oxidized. So in order for a reaction to happen, the guy that gets oxidized have to be higher on activity series than the one that gets reduced. Now we know that H2 is going to do my oxidation, right? H2 is going to be my oxidation. So these guys that are going to get reduced, that's not going to happen, because the one that gets oxidized has to be higher on the activity series than the one that gets reduced. So then these ones right here, they would actually happen, because this is oxidized and these are reduced. These are below that. So H2 on top and these are on the bottom. So these would actually go. So when you look at the activity series, first of all, figure out what's been oxidized, what's been reduced. And the guy that has been oxidized has to be higher on the activity series than the one that has been reduced. I made a couple videos going over the activity series. Make sure you watch those so you get the concept down. So which one are going to be is going to react with silver and Hg plus 2 and copper, because these are getting reduced and this one is getting oxidized. This one is on top, these are on the bottom. All right, the least conductive water. What do you think? Deionized water, right? That's the expensive type. You filter the heck out of it. It doesn't have much calcium and and iron and other stuff in there. So the least conductive water would be the pure water, right? Because you've taken all those electrolytes out of it. So we deionized water. Tap water, oh, that's not going to be good. Distilled water, a little bit better. Deionized water, now we're getting fancy. So it's more pure, so it's not going to be least conductive. 2 weak acids, okay? You got this one down. What are the weak acids? Is going to be HNO2 and HClO2. You got to know the strong acid for me, okay? You got to know the strong acids. Let's go over them together right now. Okay, even though I can't hear you, tell me, what are the strong acids? HCl, HBr, HI, HNO3, HClO4, H2SO4. These are the strong acid, and everything else is considered weak. These are the strong acid, everything else is considered weak. Alright, let's move on to the next problem. Okay, for this problem, it says select the largest density. Remember the old saying, you cannot compare apples and oranges? It applies to chemistry too. You cannot compare things unless they have the same unit. You can compare apple and apple, orange and orange. You cannot compare apple and oranges. Remember that the same applies here. There's no way you can just look at it and say, I think this is the largest one. You can't do that. The only way to compare things and pick the largest or the smallest if only they have the same unit. And I need you to remember that. So to compare, they have to have the same unit. If they don't have the same unit, you have to convert everything to the same unit, and then you are going to decide which one is the largest or the smallest one. So far, so good? Okay. So these are the units that the problem has. The problem has gram over centimeter cube, kilograms over meters cube, grams over millimeters cube. I'm going to pick one unit and convert all to the same unit and then compare. What I'm going to pick, I'm probably going to pick grams over centimeter cube. So I have 1 grams over centimeter cube. I'm going to convert everything else to that. So my next one is 1 kilogram per, let me write it right. 1 kilogram per meters cube. Okay? So, again, remember, what I'm trying to do, convert everything to grams over centimeter cube. So, in this case, what does that mean? What that means is I don't want kilograms. Kilogram is going to go here. Gram is going to go on top because that's what I want. What's the relationship between kilograms and grams? You know it. 1 kilograms is 1,000 grams. Okay? Alright, so far so good. So the kilograms cancel out. I end up with grams. That's what I want. And then I don't want meters cube. I want centimeters cube. Okay? I want to put meters over here and then centimeter over here. Now, what's the relationship between meters and centimeter? 1 meter is 100 centimeter, right? 1 meter is 100 centimeter. Now, here's the problem. I am not trying to cancel out meters. I'm trying to cancel out meters cube. Now, can I just put a 3 over here and a 3 over here and then be done with it? No, don't get fancy on me. You cannot do that. And the reason you cannot do that, because 1 meter is 100 centimeter. That's the relationship, meters to centimeters. Not cube, not squared. The relationship is for meters over centimeter. That relationship would not work if I have squared or cube. So the only thing I can do is that I can cube the entire thing. I can cube the entire thing. Now, remember, if I cube the entire thing, that means meters is going to get cubed, 1 is going to get cubed, 100 is going to get cubed, and centimeter is going to get cubed. Everything is going to get cubed. Pay attention when you're doing the math. So, in that case, what that means is now I can cancel out cubic meters, and what I end up with centimeter cubed. All right. Again, remember over here, this is not 100 anymore. This is 100 cubed. So if you do that, what you end up getting for an answer, you get 0.001 grams over centimeter cubed. Perfect. Okay. Now, then my next one is I have 10 grams over millimeters cubed. Okay. Again, keep your eye on this. What I want is grams over centimeter cube. Gram, great. So I don't have to do anything. So the only thing I need to change the millimeters cube. So I don't need to do anything with a gram because I want gram, but I don't want millimeters. What do I want? Centimeter. So the millimeters goes on top. The millimeters goes on top and the centimeters goes on the bottom, so I can cancel them out. And what's the relationship? 1 centimeter is 10 millimeters. You got to know those metric relationships. Go back to that lecture. 1 centimeter is 10 millimeters. Now remember, again, we're not trying to cancel out millimeters. We're trying to cancel out millimeters cube. I can't just put a 3 here, because the relationship is 1 centimeter is 10 millimeters. There is no cube or squared. So the only thing I can do is what? The only thing I can do is put a cube outside this. Okay? All right, so this is good. Now we're talking. So I already had gram, didn't have to do anything to the gram. Now the millimeters cube is going to cancel out, and I end up with centimeter cube. So if you do that, what you end up getting is 10,000 grams over centimeter cube. Now that everything is the same unit, I can compare. Because everything is in the same unit, then now I can compare. Before we couldn't compare. Now we can compare. All right, now tell me, what is the largest density? What is the largest density? The largest density is going to be this one right here. Yeah? All right, beautiful. Next one. In this problem, it says the one that represents the smallest number of F atoms. Hold on a second. Didn't we do a problem just like this? We did. Let's go back to this one right here. Right here it says the one that contains the smallest mass of fluorine. Yeah, it's just like that. Now again, we have to do the same thing. Over here, we had to convert everything to mass of fluorine and then compare and then pick the smallest mass of fluorine. Exactly the same thing here. We're going to get more practice. So to pick the smallest number of F atoms, we would have to convert everything to F atoms and then pick the smallest one. All right, so we know how to do this. You ready for this? Let's do this. Now, before we do this, I want to show you this one more time. Remember, this is the conversion. Gram to moles, molecular weight, moles to atoms or molecules or ions, Avogadro's number, and you can go forward and backward. And don't forget, when you have one thing, but they ask you for something else, hashtag mole ratio is what you need. Hashtag mole ratio is what you need. When they give you one thing, but you need something else. All right, ready to do this? Let's do this now. Now, I'm going to convert everything to fluorine atoms. The first thing I have 0.5 moles of F2. Okay, so what I got to do, I got to convert it to atoms of F. All right, I already have moles. This is great. I already have moles, so I can do my mole ratio. I like that. Now, right here, I don't want the moles of F2. What I want is moles of fluorine. What is my mole ratio? In 1 moles of F2, how many F you have? You have 2F. All right, so I already did my mole ratio. That's good. So now I have moles of F. I have what I want, which is F. Now what I want atoms of F. So what I'm going to do, I'm going to convert moles to atoms. 1 mole of F would be Avogadro's number, 6.02 times 10 to the 23rd. So when I do that, what I end up getting is 6.02 times 10 to the 23rd atoms of F. So it was already moles. I did a mole ratio and then converted to atoms. Okay, ready for next one? Let's do next one. Next one is we have 6 times 10 to the 23rd molecules of F2. Okay, molecules of F2. Now, there is a shortcut to this, but I'm going to do it a long way just because I want consistency, and then I keep talking about the mole ratio. So I've given you F2, but what we really want is F, right? So what I'm going to do, I'm going to do a mole ratio, but before I can do a mole ratio, I need moles. So I'm going to convert this to moles. 1 moles of F2 is 6.02 times 10 to the 23rd molecules. Okay, again, what I'm doing, I'm converting molecules to moles so I can do a mole ratio. So the molecules cancel out. Now I have moles. Now that I have moles, can I do a mole ratio? Now I can do a mole ratio. I don't want the moles of F2. What I want is moles of F. Okay. All right. So what is the relationship between two? We talked about it. In 1 moles of F2, you have 2 moles of F. So far, so good. Okay. Now that we have moles of F, what I'm gonna do, again, we want atoms of F. So we're gonna convert it back to atoms. 1 moles of F is 6.02 times 10 to the 23rd to convert it back to atoms. So what I end up getting is 12 times 10 to the 23rd atoms of F. Now, I know some of you guys are looking at me and it's like, what did you just do? So I wanted to go back to the basic. What I have taught you was if I give you one thing, I want something else, mole ratio. Now, in order to do mole ratio, you need to convert it to moles. And that's what I did over here, right? I converted to moles, I did my mole ratio, and then I converted to atoms that the question asked for. Now, if you look at this, this was very redundant, right? This was very redundant. All I had to do, just do the ratio over here, and I would get the same answer. And if you did that, that's great. But I wanted to do it a long way, in case in case you want to see how we did this. Again, if you didn't do this at all, if all you did was just, okay, there's a 2-to-1 ratio and that gets you the answer, that's great. But I wanted to do the long way since I've taught you the mole ratio so you don't get confused. Ready for last part? The last part is 57 grams of F2. Okay, this is the same as before, 57 grams of F2. What am I going to do? I'm going to convert this to moles. 1 mole of F2 is 38 grams. Okay, so the grams cancel out. Now I have moles. What am I going to do? I'm going to do a mole ratio. 1 mole of F2 has 2 moles of F. You know that already. Okay, so again, I had gram, I converted gram to mole. Once I converted to gram to mole, then I could do a mole ratio. Okay, so now I have moles of F. That's great. Now, what does the question ask me to do? It asked me for atoms. So I'm going to convert moles to atoms. 1 moles of F is 6.02 times 10 to the 23rd. So I can get atoms. If I do this, what I end up getting is 1.8 times 10 to the 24th atoms of F. So far, so good? Okay. Now, we converted everything to atoms of F. Now we can compare. So which one represents the smallest number of F atoms? Which one represents the smallest number of F atoms? Now that we converted everything to the same thing, it's super easy to pick which one is going to be. Which one is going to be? The answer is going to be this one right here. The first one, this is going to be the smaller than the other two. Yeah? All right. Again, if you have a question like this question take a long time. This question take a long time. I would do this at the very end. But I wanted to do this because this was a good practice problem to go between gram and moles and atoms and do a mole ratio to make sure you get that down. All right, let's move on. Okay, so the next question. Oh, I missed one. I forgot J, didn't I? Let me do K, and then I'll do J after that, after this one. Clearly, I do not know my alphabet. So two solutions, again, don't get confused. There is J before this. I forgot to write it down, but again, I will go back to that one. So two solutions that are not conductive. Not conductive. Okay, what does conductivity has to do with anything? Tell me. Remember what we talked about. When you have free ions, you are conductive. So when it talked about conductivity, you have to look at solubility rules. So when we talked about conductivity, you have to talk about solubility rules because free ions are conductive. You have to see if based on the solubility rules, they would break up into ions. And if they break up into ions, then they are conductive, right? Ions, then they are conductive. Solubility rules will be given to you on the exam, okay? Just make sure you know how to use the solubility rules. So two solutions that are not conductive. So if you look at over here, we have magnesium sulfate. Magnesium sulfate is the first one. So here the sulfates. The sulfates are soluble except if it's next to copper, silver, gold, mercury, Pb plus 2, barium, Sr plus 2, and Ra plus 2. Magnesium is not one of them, so magnesium sulfate is going to be soluble. It's going to break up into ions, is going to be conductive. FeCl2. What do you think? FeCl2. I don't have a rule for Fe. I do have rules for halogen. Chloride, bromide, and iodide are soluble except next to copper 1, silver 1, gold 1, mercury 1, and Pb plus 2. Okay, yeah, Fe is not one of them, so yes, that's also soluble. So far so good. All right, copper hydroxide. There's a rule for hydroxide over here. Hydroxide are insoluble now. They're insoluble except if it's next to one of this. Copper is not one of these, so that is going to be insoluble. Hopefully you follow me so far. Now, MnSO3, there is no rule for manganese, but there is rule for sulfite right over here. Carbonate, phosphate, silicate, sulfite, chromate, they are insoluble except if it's next to 1A or ammonium. Well, it's not. Right now, sulfite is next to Mn, so that is also going to be insoluble. So solubility rule will be given to you on exam. Just you need to be able to use it and read this. Remember, find the rule for the one that has a rule over here, and then look through what are the exceptions and what makes it to be soluble and insoluble. So far, so good. All right, beautiful. Let's go to next one. In this problem, it says the number of moles of phosphoric acid required to completely react with 1 mole of barium hydroxide. What do you need for this? You need a balanced reaction. You need a balanced reaction to see what is the mole ratio. So what we need a balanced reaction. We have phosphoric acid that is reacting with barium hydroxide. What we need before we can figure this out, before we can do a mole ratio, we need a balanced equation. We need a balanced equation. This is a double replacement reaction. In is with in is and out is with out is. I know you know this, so I'm just going to write the final product. What I end up getting is Ba3PO4 2 plus, don't forget, when I have H and OH, what do you get? I get H2O. So I need a balanced equation between phosphoric acid and barium hydroxide. Double replacement reaction. You know double replacement reaction. I know you know. So you're going to do the double replacement reaction, and then you are going to balance this equation. Then you are going to balance this equation, and now you have a mole ratio. You can do this problem. Now, technically, this is a titration problem, right? You have an acid and base. But this is harder to see the mole ratio in this titration problem because none of them are mono. This is not mono, it has 3 hydrogen. This is not mono, it has 2 OH. So balanced equation is the best way to go. Again, this was a double replacement reaction. I did a double replacement reaction, and then I balanced the equation. Now I can do this. So they said you have 1 mole. They say you have 1 mole of barium hydroxide. Okay, you have 1 mole of barium hydroxide. Now what you want to figure out the number of phosphoric acid that is, the mole of phosphoric acid is required. Well, we have a balanced equation to do a mole ratio, so I don't want the mole of barium hydroxide. What I want is mole of phosphoric acid. What is the mole ratio? What's the mole ratio? 2 phosphoric acid for 3 barium hydroxide. So I have 2 over here and then 3 over here. So far so good? Okay. And then the barium hydroxide would cancel out. I end up with phosphoric acid. I did my mole ratio. What I end up getting is 0.67 moles of phosphoric acid. And that is one of the options, which always makes me happy, right here. Again, what I needed a balanced equation to figure out the mole ratio. And this is, like I said, the titration problem. It's like a first problem we did, but it's harder to figure out the mole ratio because none of them, this has 3 hydrogen, this has 2 OH. So the best thing I can do is a balanced equation. All right, let's keep going. Nice job so far. Now, over here, our next problem, we have a density problem. And don't worry, I'll go back to that J problem that I forgot. So I have a density problem. Now, you know what density is. You know this. I know you know this. You know that density is mass over volume, right? So we know that density is mass over volume. Do you have the mass over here? The mass is given to you. Is 9.0 gram. Do you have the volume? They don't give you the volume, but they give you the water displacement. If you remember, the water displacement would be the volume. So what happened to the water displacement even from 6 to 11, right? So 11 minus 6 is going to be the volume. So again, what they give you here, they give you the water displacement. It goes from 6 to 11. So 11 minus 6, that's going to give me my volume. So what my final answer is going to be 1.8. Again, you know density. What is density? Mass over volume. And then you plug it in from over there. Then you plug it in from over there. And I don't give you the volume here, but I give you the water displacement. The water displacement is the same thing as the volume. It's another way to figure out the volume. All right, beautiful. Now the next one is so funny because so many people miss this question, even though it's supposed to be one of the easiest questions on there, because there's a tricky part to it. The color of phenolphthalein in HCl. Everyone immediately says pink. Not everyone. A lot of people say pink. But remember, when you add the phenolphthalein to the acid, it was clear. When you add the base to it, that's when it turns pink. So phenolphthalein in acid is clear. In base is pink. You guys got this down? So remember, phenolphthalein changes color when the solution is basic. So if you add phenolphthalein to anything that is acid, it's going to be clear. If you add phenolphthalein to a basic solution, then it's going to be pink. When it turns pink, that's when your solution turns basic. You didn't have any more acid in there left. So yeah, everyone wants to just say pink, but no, it's actually clear because phenolphthalein in HCl in acid is clear, in base would be pink. So far, so good. All right, beautiful. The color of MgCl2 solution in lab. If you remember, the color of MgCl2 solution in lab was clear. So the Mg in lab was clear. And sometimes you can use the color to figure out what you have. And you had a redox lab, I think, that you do this. And then you had to figure out the bottle and match up the bottle. But if you know the color sometimes, the color helps you to match up the bottle. So yellow, what was yellow? When you have yellow, you have iron. What was blue? When you have blue, you have copper +2. So if you remember to that lab, yeah, you had bottles and you had to match it up. If some of them have color, when things have color, that's nice. That helps you to figure out what you have. If I see a blue solution and I know copper +2 is one of the options, that's going to be my copper solution. If I see a yellow solution and iron +2 is one of the options, that's going to be my iron solution. And Mg was clear. Mg +2 is a clear solution. All right, nice job. Let's keep going. In this question, it says your data is considered to be what if the values are close to each other? Remember, if the values are close to each other, that is considered to be precise. Okay? Now, how about accurate? I need you to remember this. Just because you're precise, just because your values are close to each other, doesn't mean you are accurate. You can be precisely wrong, right? Doesn't mean you're accurate. How do you know you're accurate? You know you're accurate when you know what the value is supposed to be and you compare the value that you have to the value that is supposed to be. So you don't know if you're accurate unless they tell you what the value is supposed to be. Yeah? All right. Beautiful. Next one. The moles of sodium hydroxide in 400 ml of solution, that is 0.14 molar sodium hydroxide. Now, you see molarity. I know you know how to do this. Whenever you see molarity, what are you going to do? You're going to say molarity is moles per liter and then plug it in. You see molarity, you go molarity is moles per liter. This is not a dilution problem because the concentration is not changing. So, whenever you see molarity, there are two equations you know. Molarity is moles per liter. The other one you know, M1V1 equal M2V2. We use M1V1, M2V2 when the concentration is changing. In this problem, nothing is changing. No concentration is changing. That means it's straight up molarity is moles per liter. Okay, I can just plug it in. I know how to do this. So in this problem, they give you the molarity of sodium hydroxide. They give you the molarity of sodium hydroxide and they give you the volume. And they ask you for moles. I can do that. I have the molarity and I have the volume. I can plug it in and I can get moles. So I have, so the molarity is 0.14. I don't know moles. Now remember, the volume has to be in liters. For molarity is moles per liter. So the volume has to be in liters. And what I get for X, I get 0.056 and X is my moles. So molarity is moles per liter. Molarity is moles per liter. One more time. M1V1, M2V2. You use this when there is a dilution. You use this when there is a dilution. What do I mean by dilution? When the concentration is changing. Dilution, concentration is changing. And for M1V1, M2V2, units don't matter as long as they're the same unit on both sides. But molarity has to be moles per liter. All right, ready for next one? Let's do it. Now, this one, I'm hoping you haven't forgot about this. But when you look at this, what type of problem is this? When you look at this, it's been a little while. When you look at this, what type of problem is this? This is a percent composition. Even though I can't see you, I can see your faces right now. I can imagine your faces saying, oh, no. Percent composition. We went over this. You know the rules for percent composition. We go percentage to gram, gram to mole, and then you divide by the smallest number of mole. You guys remember that? Gram, percentage to gram, gram to mole, divide by the smallest number of moles, and then you get a ratio. That's exactly what it is, and it's exactly what you did in lab, for the hydrate lab. Okay, so what this problem is telling you is that, remember, I have percentage to gram. So the first thing I'm going to do, I'm going to say I have 73.42 grams of ammonium phosphate. Okay. Now remember, the entire thing has to be out of 100. So how much water do you have? So the water, I would have to subtract it from 100. So 100 minus 73.42 is going to give me 26.58 grams. So percentage to gram, but remember, it has to be out of 100. They have to add up to 100. So if it's not, if you don't have one of the molecules, you can subtract from 100 and figure out the percentage and percentage to gram. So far so good. So the hydrate has a hydrate and has a water. This one right here, ammonium phosphate, is 73.42%. Subtract by 100, that gives me water. And percentage, I can just say that's gram because it ends up being 100. So percentage to gram. Then I have to, what's the next thing? I have to do gram to moles. I have to do gram to moles. We know how to do this. How do we do this? Molecular weight. 1 mole of ammonium phosphate is 149 grams. So I get 0.492 moles of ammonium phosphate. Water, okay, I have the grams of water. Again, molecular weight of water is 18 grams. I can do grams to moles using molecular weight. I get 1.476 moles of water. Percentage to gram, gram to moles. Now divided by the smallest number of moles. What is my smallest number of moles? 0.492 is the smallest number of moles. If I do that, I get 1 over here, I get 3 over here. That is my ratio. That is my ratio. Okay? So they ask you for X. They ask you for how much water do you have. The answer would be 3. Again, this is percent composition. Again, percent has to be out of 100%. Percent to gram, gram to moles. Divided by that, and you get a ratio. Okay, let's go to the next one. This question is double replacement reaction. You know double replacement reaction. Show me on the lab exam that you can do this. Now, this one is a little bit harder because I don't give you the actual formula. I just give you the name. So let's do this. You know how to do this at this point. Ammonium chloride. So ammonium is NH4, chloride is Cl. Ammonium is +1 and Cl is -1. So this is already balanced. This is already balanced. Okay. Now, the next one, lead 2 nitrite. So Pb, nitrite, and NO2. Remember, Pb is +2. They tell me is lead 2 because it could be, it has a transition mineral, it has different charges. They tell me is lead 2, so +2. Nitrite, a polyatomic ion. Nitrite is -1. So what I'm going to do, I want to cross multiply the charges. We don't write the 1, so the 2 goes over here. Okay, I'm hoping at this point you guys are really good at this. You got this down. All right, so here are my compound double replacement reaction. In is with in is and out is with out is. In is with in is, out is with out is. Doesn't matter which one you write first. Doesn't matter which one you write first. So ammonium is going to leave Cl, is going to go and hang out with NO2. So NH4 is going to leave Cl, is going to go and hang out with NO2. Remember, ammonium +1, nitrite -1 is already balanced. You need to make sure all the compounds are balanced. All right, now my inis. Cl is going to leave ammonium, is going to go and hang out with Pb. But I need to write the cation first and then the anion. Cation and then the anion. So I have to write the Pb first and then I write the Cl. Pb, we know is plus 2. The question told us is plus 2. We know Cl is minus 1. We're going to cross multiply the charges. We get PbCl2. Okay, so this is good. I balance out the two equations. Now I have to balance the entire formula. The entire equation needs to be balanced out. So how do I do that? Let's see. What we have over here? We have 2Cl over here. So I would have to put a 2 over here. If I put a 2 over there, now I have 2 ammonium. So put a 2 over here. Yeah. Now it's balanced out because then I have 2 nitrite, 2 nitrite. Life is good. Molecular formula. Now, for total ionic, remember what we said. When you add two things together, nothing will happen. What do you need to make a reaction go? You need water as a medium to make a reaction go. Because of that, we have to see what happens to each of these compounds in water. What do we need? We need solubility rules. Let's take out the solubility rules again. Here is my solubility rules. Okay, so the first one is ammonium chloride. What happens to ammonium chloride in water? Ammonium chloride, I have a rule for chloride. Chloride, bromide, iodide are soluble except if it's next to one of those, and ammonium is not one of them. So ammonium chloride is going to be soluble, it's going to break up. Now when you break up, you end up having 2 ammonium and 2 Cl because they break up into ions. Now, putting out the charges is very important. If you don't put the charges, you are going to lose point because when you break up into ions. Okay? And remember, because I have 2 ammonium chloride, I have 2 of them, when everything breaks up, I end up with 2 ammonium and 2 Cl minus. So you break up into ions. Don't forget that. All right, next one. Lead to nitrite. There is no rule for lead, but nitrite. Check over here. Nitrate, nitrites, acetate, and chlorates and iodates, they're soluble, no exception. So yes, this is going to be soluble. It's going to break up into ions. So I'm going to get Pb plus 2. Now, again, when this breaks up, how many nitrite do you have? You have 2 nitrite. You have 2 NO2 minus. One more time, you break up into ions. You have to put the charges. And I know you know this, but just for my own good, I want to make sure you really understand this. So here, if I were to draw it out, you have a Pb plus 2 and you have 2 NO2 minus attached to it, right? So when everything breaks up, you end up having 1 Pb and 2 of these nitrite. 2 of these nitrite. So you have to pay attention to that. So far, so good? Okay. Now, let's go to the product. The product, I have ammonium nitrite. Does that break up? That breaks up. We just said all the nitrite, they break up. They have no exception. So I have 2 ammonium and 2 nitrite. Again, don't forget that what you are doing, you have these charges. Don't forget, they're going to break up into ions. Don't forget the charges. And why do I have 2? Because I have 2 ammonium nitrite. So when everything breaks up, I have 2 ammonium and 2 nitrite. Lead to chloride, does that break up? Let's see. So Cl's, chloride, bromide, iodides are soluble except next to copper 1, silver 1, gold 1, mercury 1, Pb plus 2. Ooh, Cl is next to Pb plus 2. That's an exception. So that is not going to break up. It's going to stay together. All right, next thing we're going to do, we're going to cross out the spectator ions. Those are the ions that look exactly the same on both sides. Exactly the same. What are they over here? Let's see. Nitrite, I have 2 NO2 minus, 2 NO2 minus. Anything else? 2 NH4 plus, 2 NH4 plus. So I'm going to write out what's left. What's left is 2 Cl minus. Now I'm going to put the phases. AQ. Anything that is soluble in water is going to get AQ. Plus Pb plus 2. Also AQ because it's soluble in water. It also dissolves in water too. Anything that did not break up I'm going to give it solid. Okay, so for the last one, don't forget, for net ionic, put the phases on. Okay, that makes sense. Pretty good so far. Now, the last thing I ask you to do, about conductivity. Now, here's what I need you to remember that. To do the conductivity, you have to look at the total ionic and not the net ionic. And I'll tell you why in a second. Now, conductivity has to do with the number of ions. The more free ions you have, the more conductive you are. It has to do with the number of ions. So pay attention to this very closely. NH4 is an ion, right? How many do I have of that? How many do I have? I have 2 NH4 plus. I have 2 ions of NH4 plus. Cl minus, is that a free ion? It is. It has a charge. I have 2 of that. 4 so far. I have 1 Pb plus 2, and I have 2, what did I just do? And I have 2 NO2 minus. Again, what I'm looking for, the number of ions. It doesn't matter what the charge is. If they have a charge, they're an ion, how many do you have? So I have 2 ammonium, I have 2 Cl, I have 1 Pb plus 2, and I have 2 nitrite. So 1, 2, 3, 4, 5, 6, 7. I have 7 free ions. What I mean by free ions, these are an ion, it has a charge. These are free ions. Okay, now help me out. Look at the product together. Right, look at the product. Ammonium plus 1. This is an ion. This is a free ion, right? So I have 2 of that. And I have 2 nitrite ion, NO2 minus. Is this an ion? This is not a free ion. This is a solid. It has no charge. So 1, 2, 3, 4. I have 4 free ions. So the ones that have charges, those are my ions. And remember, conductivity has to do with ions. Because ions have charges, they carry electricity. Ions have charges. Charges carry electricity because electricity is also negatively charged. So what happened? I went from 7 free ions to 4 free ions. I have less ions. So what happened to conductivity? The conductivity went down. Now, why did I look at the total ionic and not the net ionic? So remember how you cross out the spectator ions? Sure, you cross it out on a piece of paper, but in reality, in the solution, they're still there. Yeah, they didn't find a partner, they didn't form a solid, but they're still floating around in a solution. Even though we cross it out here conveniently, in a solution, you can't just cross those out. Those ions exist in the solution and they add to the conductivity because they're free ions. And one more time, what you're looking for, you're looking at the number of free ions. It doesn't matter what the charge is. This is not redox. It just matters if it has a charge, how many of that ion do you have? All right, beautiful. Now there was one question I forgot to do. Let's do that one and we are done. All right, so this is the one that I forgot to do. I skipped this one. Now, remember that we talked about hydrate in lab? You probably talked about hydrate. What's a hydrate? A hydrate is when you have a salt plus water, right? You have an ionic compound, you have a salt plus water, that's an hydrate. Now, if in here, they give you the percentage of water. So again, percentage is a gram percentage, right? So what that means is grams of H2O over the grams of the hydrate times 100, that's going to give me 31%. Because again, it's a percent of water in the hydrate, right? So water over the hydrate times 100, I have 31%. You follow me so far? Okay. And remember, percentage is usually gram percentage. So they give me the percentage of water over the hydrate times 100, that should be 31%. I want to get rid of the percentage. So what I would do, I would divide by 100, right? I would divide by 100. So then what I would get 0.31. Okay? So then water over the hydrate is going to equal 0.31. All right. Now, what's the other piece of information they gave you? Grams of the hydrate. Okay, so that's great. So I'm going to put this in. So I don't know the grams of water, but the grams of the hydrate is 3.0 gram, equals 0.31. So if I solve for x, it's going to be 0.93 grams. What is that? That would be the grams of water. Follow me so far? So you have to use what they give you. They give you the percentage of water and they give you the grams of the hydrate. Remember, percentage is usually what? Is usually gram percentage. So what that means is grams of the water over the grams of the hydrate times 100, you get 31%. We divide it by 100 to get rid of the percentage. So grams of water over the grams of the hydrate equal 0.31. I have the grams of hydrate, so now I can easily solve for x, which is my water. Except the question doesn't ask you for grams of water, it asks you for the mass of salt. Now, let's go back to the top. What did we say? We said a hydrate is what? A hydrate is salt plus water. Okay? Now, I know that my hydrate is 3.0 grams. I know my water is 0.93 grams. So can you figure out the salt? Yeah, you can figure out the salt. The salt is going to be my x. And if I solve for x, I get 2.07 grams. And that's one of the options. Okay, really nice job. I know this was long. We went over a lot of questions. And keep doing the problems and make sure you know every question. Come to office hours if you have any questions. And good luck on the lab exam. You got this.